let's see what we can say about inverses. What is an inverse? What do we mean by an inverse? Someone give a definition for us before I give one up here. What do we mean by an inverse? What is that? Can you do a little recall? Yeah. Yeah. I mean, by definition, if we have some relation that pairs A to B, then the inverse pairs B to A, right? That's the definition of what we mean by an inverse relation. And when will that relation be not just a relation, that inverse relation, when will it be a function? That's a good question to ask. This should be just like peppering you with review questions right now, but I promise, as usual, we'll take this to a level deeper, just like we did yesterday. Hopefully we made good on that promise that we did yesterday. Took to the next level. So I promise we'll get around to this. But this is not them yet. This should be something that's review. When is the inverse relation going to be a function? Go ahead. Okay, yeah, if the original relation is a function, then we require that it be something called a one-to-one function. Supposing the original relationship isn't necessarily even a function, what test can we apply, though, to ensure that when we take the inverse of that relation, it will be a function? Yeah, the horizontal line test. You're right. If we want to require both the vertical and the horizontal line test to pass, then we have something called a function, and it's a one-to-one function. So just as, I'll seriously give you like 20 seconds, I want to ask you in your group, just go through and answer real quick. Which of these are functions, and then also, if you were to take the inverse, which would be functions? So figure that out real quick, and 20 seconds later we'll... All right, time. Let's come back together. You guys are chatting wonderfully. Good on you. Okay, first question. Which one is? I'm going to go through and you're going to say yes or no. Function. The first question is this a function?
Yes. No. No. Yes.
Okay, and what about if we take the inverse of these, will they be functions?
Yes. Yes. No. No.
I love that. That was cool. I heard no disagreement. I didn't hear like among the chorus of no's like a yes or anything. That was good. But that's okay. We can explain. Oh, excuse me while I clear the annotations from my previous class. That would be like destroying the mystery and the wonder. All right, I think we're good. All right, good. Woo. That was close. By the way, it should make sense. That we need to pass the horizontal line test because when we do the inverse, the new function has to pass the vertical line test once you do the inverse. So before you take the inverse, it should make sense that it has to pass the horizontal line test. We'll say more about that in a second. And then let's say what Grant said, and that's if we demand that a function have an inverse that's a function, then we're talking now about a one-to-one function. And if you like the language of vertical and horizontal line test, then we're talking about a function that passes both, right? A relation that passes both. So this is said basically the same way, but now using function notation, right? By the inverse function, we mean the unique function that takes, if the original function takes A to B, then you better mean, by the inverse, you better mean the function that always faithfully takes B to A, whatever A and B might be. And of course, let's say it one more time, it's not necessarily true that this is always possible, right? In order for this to be, for there to be an inverse function, the big question, the big hypothesis is right here. If f is 1-to-1. All right, so when you're ready, let's try this algebra. I just, by the way, assume that you're familiar and comfortable with the mechanics of actually finding the inverse. So I'd like you to try this one. Again, I try to promise you that we're going to take it to the next level. I think this one does that for you. The algebra here is non-trivial, but I think you can do it. By the way, I guarantee this is a one-to-one function. I'm not just trolling you. This does have an inverse, okay? You just need to try hard. Like, take a minute or two to do this. I'll be looking for someone who can actually produce the algebra here. And I'll get you. Good. Don't be discouraged. The algebra of the little chicken. Good. Right here. Don't look up here. Person next to you about the idea is you kind of know where you're stuck. What do you do then? All right, the missing piece of algebra that I think most of you successfully got to here, maybe, right? So she switched x and y, I guess we can say that, and then she is attempting to solve for y, which is what you did too. I think you probably did this, didn't you? But then, do you see this move here? This is the clutch move right there, right? Right there. Bam, bam. Now, and then you're good, right? Now let's just express this in the nomenclature that was introduced in the problem. F inverse of t is equal to t over 1 minus t. And the domain and range are, let's hear from people on that as well. What's the domain for this inverse function, that is? Is there anything t can't be? Yeah, t can't be 1. And what about the range? Is there anything that y can't be, or is it all reals? What's the? What'd you say? Can't be -1. Can't be 0. Which is it? I don't know. You want to explain any of those people who just offered an answer? Yeah. Oh, okay. So the domain of this guy, the original function, is t isn't -1. So that means the range isn't -1 for the inverse. Check out this line of the thing up the top. If you thought that was just mumbo jumbo, it does actually say something up there, right? The domain range should switch. So if you can answer the domain question for the original function, then you can certainly answer the range question for the inverse function. Anything else you want to say about that? Okay, I heard some people mumbling about this a second ago, but do you know there's another property of inverses that you might have explored last year in the algebra class, and that's a relationship graphically between the function and its inverse. What is that? Yeah, there's a reflection available to you that maps one to the other. It's called the inverse reflection principle, and it is. It's over the line y equals x. So I do hesitate to say this a little bit because obviously it doesn't always make sense to reflect a graph over the line y equals x and have it plot that on the same grid. For instance, consider if I have a graph like this, say, I don't know. Now I'm choosing D and T very intentionally. Does it make sense to show the inverse of this function on this coordinate system? The inverse looks something like this, and if you plotted it, I mean, you certainly could plot it here, I guess. The inverse looks something like that, right? It certainly makes sense to take the inverse of a distance time graph, right? You might want a function that takes distances and returns times. That's fine. But what's the problem with that picture, though? Plotting them on top of each other, in this case, in the context of the problem. Say something. Yeah. Yeah, Tigers. Right, yeah, the axes are like confusing. Like we can't have both work at the same time, kind of. And that's also because what else happens when you do a reflection over the line y equals x? Well, the function itself switches, right? Reflects itself. What else reflects? What's the image of the x-axis under the reflection over the line y equals x? Well, it's the y-axis, right? So they exchange places like that. So it's a little weird to graph them sometimes in the context, but it certainly is true that if you were to do this, here I'm using just y equals x squared and the square root of x to demonstrate this. But it would be good, this is just one example, and I think someone told you this, or maybe you observed it through a bunch of examples, and you're like, yeah, this seems to be true. But I would challenge you to prove this fact. Why is that hold? I mean, maybe you've never challenged yourself in that way. Is it always true? How can I prove it geometrically that AB is the reflection always of BA? It's an interesting question, so I'll let you think about that if you haven't ever proved that. And now, practice another one here. Find another inverse. And then when your life is changed, say, oh, something like that. Mind blowing. Look, no, you didn't actually do it yet. Good job. Wow, that quick. Well, it may have something to do with the warm-up, that's true. But did you find the inverse yet? Did you say aha? Yeah. Aha. So what's the inverse? Same. What? Same what? Allow me to go back to the warm-up for just a second here. There it is. So, why visually is that happening for this equation? Or, said another way, why algebraically was it happening when we had our lazy people who just said, oh, 4, 3, well, 3, 4 works too, just looking at the equation. Visually, when would we expect this to happen? When the original graph has this symmetry already, that has symmetry over the line y equals x, doesn't it? So it's reflection over the line y equals x itself, isn't it? Can you think of other functions that do that? Y equals x, certainly. Anything else? Any other? Y equals negative x works. Can you guys think of any other non-trivial functions? Yeah. 1 over x works, too. Is its own inverse. Sure. And you can try and think of other functions that do that as well. So good job. Another property of inverses that we want to discuss is the inverse composition rule. And this, again, sometimes people get lost in the notation and the language and the technical definition here. But it should just make sense that if f and g are inverses, and you do something to x by way of g, and then you take the result of that and apply f to it, Well, if f is designed to undo the actions of g, then it should make good sense why the resulting action is just you doing nothing. This is the identity function, right? What happens if I do something and then undo it? Well, that's basically you doing nothing, and isn't that what x is? The identity function. Or said another way, yeah? Here, x is maybe an unstable piece of paper. Okay? You like the picture? Okay. I think I'm gonna have one of my aides, one of my math department aides do this. If you could just staple all this stack of papers, that'd be great. And then afterward, if you could just here's a staple remover. If you could just go through and remove all the staples, that'd be great. They'd be like, wait, you want me to do nothing? There is a small caveat here, yeah. Maybe the paper we start with has to already have 2 holes in it for this to really work for it. Maybe the staple remover also has like a hole filling property too. I don't know. It's not perfect, but it is cute. Come on, right? Are you done? Drawing the staplers yet? You do have to draw the stapler in your notes, right? Okay. Let's try it with a function here. What I'd like is, just for the sake of time here, have everyone on this side of the room, over here. Why don't you guys do f of g of x? Everyone over here do g of f of x. And see if the desired thing happens. Okay? And in the middle, you guys can do whatever you want. F of g of x over here. G of f of x over here. For these people. For these people. Why do I need the x greater than or equal? It's negative 2. Did it work? I mean, you don't need me to check your answer. You'll know if you got it. You got it, right? Why do we need the x greater than or equal? Yeah, why do I have to restrict the domain of d?
Not that
Yeah. So yeah, I need g to. What was wrong with g to start with? Nothing. Did you guys figure out why you need that greater than or equal to? You guys do the other one? If you're done, you can try the other one too. I forget which one's easier. If you've done one, try the other. And also, like I said, think about why I placed that domain restriction on G. If you haven't explained that to yourself yet. Why did I have to do that, really? For this to be like
I didn't get it. You got X. You got X.
I guess we won't write these up here since you know, if you got it, you got it, right? I mean, you got X. So if you'd like to see the work, we can put it up here. All right, yeah, so why is the x greater than or equal to -2 there? Someone wanna, what was wrong with g? Like, why couldn't I have just given you g of x as it was? What's wrong with g that requires, like, some fixing? Yeah, that's the square root has a limited domain, is that what you say? And range, okay. I mean, that's getting at the idea, yeah. Remember, what kind of function has an inverse? Does g have an inverse? Under what conditions does a function have an inverse? If it's 1-to-1. If the only way, and was this 1-to-1 before? No. In fact, a garden variety parabola, off-the-shelf parabola, this doesn't have an inverse as a function, does it? But this one does because of the domain restriction. Now I have a function. And I do actually have a function. Before we go, Varun, can you just tell us one thing you learned today that was like mind expanding? Because I know you knew about inverses before, so I just, was there anything? Okay. Have a great day, guys. Homework 5 from the book tonight, please, if you will. See you on tomorrow.